The Vercel AI SDK is a TypeScript-first toolkit for building AI features. It streamlines text generation, embeddings, and structured outputs. In this course, you will learn how to use the Vercel AI SDK to create and ship a customer support agent that makes autonomous decisions to either answer questions based on your support docs or search the web in real time. Mayo from Scrimba developed this course.
Welcome to the course on building a customer support AI agent with Vercel AI SDK and OpenAI. Now, over the past couple of years, we've seen how AI has transformed how we work. And one of the most exciting recent developments is the rise of AI agents. This allows the large language model to not be static, but be able to trigger these different actions and make more autonomous decision making, thereby giving us more productive results. In this course, you're going to dive deep into the various strategies to help you build a production ready AI agent. We will be focusing on the use case of customer support to make this learning process easier for you. Now, we've seen the use case of AI as a chatbot where you ask a question and you get a quick response. But as I said, AI can go much further now with these agentic capabilities because of the ability to take action and call APIs and get into databases and do things like booking hotels online, interacting with websites, debugging code, performing deep research. And so now businesses are able to use these AI agents to automate complex tasks, synthesize information, and deliver long form insights. Now, one of the most popular and powerful use cases is customer support. Why? Because customer support is at the heartbeat of every company. This is where complaints, bugs, and issues surface. And solving them well is essential to keeping customers loyal and happy. AI agents can make a huge difference here because they can, first of all, help to escalate and resolve issues quickly. Second of all, they automate responses to basic queries so the human experts only focus their valuable time on the complex cases that the model cannot confidently resolve. Thirdly, they help to personalize support by retrieving details from past conversations or user profiles. Again, this is very useful for customer retention. And finally, they can help the company analyze customer interactions, uncover trends, problems, and even new product ideas. So, in this course, you will learn how to build exactly this type of AI agent that doesn't just generate text, but intelligently routes queries, retrieves real time information, and reduces hallucination. So, firstly, you will learn how to create logic so that the large language model will intelligently classify and route the user's query based on their intent. Secondly, you will learn how to build this AI agent that doesn't only just know when, but also how to retrieve relevant real time information. You will learn the basics of using the popular Vercel AI SDK, which will help you to simplify your workflow and speed up your development process. You'll also learn the integration of retrieval augmented generation for more accurate answers, and building this customer support AI agent in the end will enable you to see and have an application that is not just QA for documents, but also the ability to perform web search and retrieve real time information from the web. And so by the end of this course, you will have a working customer support AI agent that is a powerful real world application with actual real world use cases to dramatically improve the support experience for the users of whatever applications you're working on. Now, this is what it's going to look like. Here we have asking a basic question: how do I join the Scrimba Discord? And it's going to be trained on Scrimba's help documentation. The results are shown below where the question is asked, and the user is able to view the sources so they can see what documents or what specific pages were where the answer was retrieved from. And likewise, web search showing the other side of the autonomous decision the agent can make, where the agent is able to go to the web to retrieve information because it identified that the answer was not available in the customer support docs. Now, before we dive in, you should already know these. First of all, you should know how to use the OpenAI API, how to create an account, retrieve the API, and just work with APIs in general. Secondly, you should be comfortable with just crafting basic prompts. If you've done it on the ChatGPT interface, that is fine. Third, you should be comfortable with the concept of retrieval augmented generation. Now, we are going to go through a brief refresher in this course, but I highly recommend the Scrimba course if you are completely a beginner at what retrieval augmented generation is. Fourth, the implementation of basic function calls. You should be familiar with the idea of function calling. And fifth, creating basic express servers for API routes. Again, Scrimba provides a course that you can go through as a refresher. But don't worry if you're not super expert. I will walk you through the essentials as we go along in this course. Now, this is just a brief warning. This course is quite advanced. Okay, so the code is fairly complex, and the challenges I've set are really going to make you think and work. So, at the end of each scrim, make sure you take time to play with the code I have presented and really make sure you understand it before moving on to the subsequent challenge. With that being said, my name is Mayor Oshin. I'm going to be a teacher in this course. I'm an AI engineer and educator. I'm also the co-author of Learning LangChain, published by O'Reilly. If you want to get my thoughts on technology, AI, entrepreneurship, you can follow me at Mayowa Oshin. With that being said, if you're ready to start building powerful AI agents that can make a real impact, let's get started. As discussed earlier, you should already have a basic idea of how retrieval augmented generation works and how it's used to create this question answer dynamic between a large language model and a user. Let's quickly recap. So, what is RAG? RAG is simply a mechanism where we store information somewhere. This could be a database or the web. And the user asks a question. We retrieve the most relevant pieces of information, pass it to the large language model's context. The large language model is able to give the final answer that's contextually relevant. Now, why is this important? This is important because large language models are limited to data they're trained on. So if you ask a question that's outside the training window, it may hallucinate or say it doesn't know. But with retrieval augmented generation or RAG, we can provide fresh contextual information so the model can give accurate answers it otherwise wouldn't know. So, for example, if I ask the question, who won the most recent FIFA Club World Cup? The large language model may not know. But with retrieval augmented generation, you can retrieve the fact that Chelsea Football Club beat Paris Saint Germain. And then this is passed into context of the model so it can generate an accurate response. So, where does this external data come from? Well, this is pulled from places like the web, database, local text files, and in this course specifically, we'll be relying on a vector database. This is a special kind of database designed to work with embeddings. Now, embeddings are simply numerical representations of words, phrases, or even images. So, if you plot them in this multi-dimensional space, as you can see in the diagram, semantically similar items will end up closer together. And when you ask a question, what's actually happening under the hood is we convert the text into these embeddings and then we compare them against one another in the database. And the closest ones are then retrieved as context and then passed so they can be used locally. Now, for the sake of this course, we are going to be using OpenAI's latest embedding model, Text Embedding 3 Small. It's fast, it's accurate, and it's perfect for tasks like search recommendations, in our case, retrieving support documents relevant to answer the user's question. So here's what to do. First of all, visit openai.com, create an account if you haven't done so, get the API keys, and then go back to Scrimba. Now, when you go back to Scrimba, in the bottom right corner, click on the small gear icon and add a new entry called OpenAI underscore API underscore key. This is where you're going to paste the API key and save. So at this point, you should understand what RAG is, why it's important, have a basic grasp of embedding, and have your OpenAI key ready to go. So, with that being said, let's move on to the next lesson where we'll run our first function to generate embeddings and see what they look like in action. So now we are in the code editor. I've already pre-installed the relevant libraries. At this point, you should have already saved your API keys in the edit environment at the bottom right. And so if you go to the config, we've essentially imported this OpenAI client from the OpenAI library. Everything's going to be pre-installed when you press run. So it would install everything in package.json, which is just essentially this OpenAI library. And then it will attempt to run start as well, which will trigger this file. So in the config, it checks if you save the environment variable, the API keys, and if you haven't, it's going to throw an error. We create the client, and then we import into the main file. Now, what we have here is OpenAI has a function called embeddings that allows you to create an embedding based on input text. And all we're doing is passing this text will be converted to an embedding into input, and then just console.log the results we get back. So if I click run, open here, we get the results. So this is the programmatic version of what embeddings look like. Essentially, embedding.data gives you an object that includes these different values. And it's important to see because you can see that all these unique numbers have been assigned to this block of text. And in the case of this particular embeddings model, there are 1,536 dimensions. So here you can see 3 rows, 6, 7, 8, 9, and all the way down to you hit 1,536 different items in the array. And so this is essentially what the embeddings look like for this block of text. Now, obviously, if I change the text, and when you change, just press Control S or Command S to save the changes, click run, and you'll see a different group of numbers are generated because the text is different. And of course, if you eventually just want to access just the embeddings, which we will later on to then pass on somewhere else, you essentially would need to first grab the first array here. So this is the only object inside. So again, the first item. Then you want to grab embedding dot embedding and then 0. So if I save, control save, should give a value. Here we go. So now we have the full array of embeddings, and then we can pass this, assign this to a variable, and then pass it somewhere else. So you can play around here, changing the different text just to have a feel for it. This is essentially the function that creates the embeddings. See you in the next lesson. Okay, so as discussed in previous lessons, a big part of retrieval augmented generation is the ability to store data that you need somewhere else, data that will be relevant to answering the user's question. And at runtime, we convert the question into embeddings. We retrieve by comparing the embeddings to the embeddings of stored data in a database, and then we pull the relevant documents back. In this course, we are going to use Superbase to be the vector store or vector database that will store the embeddings of these documents that you eventually want to retrieve based on the user's question. So Superbase is essentially a Postgres open source database, but most importantly, it has a PG vector extension. This is just an extension that essentially allows us to work with embeddings at scale. Go to superbase.com. Once you're in superbase.com, follow the instructions to sign up and create an account. And then it's going to prompt you to create a new organization. Just create a free plan, personal, and just give your organization a name. Once you give your organization a name, you want to go in the middle of the web page, click on create new project, and then you'll be given an interface similar to this. Choose a region, East US, or wherever is kind of closest to you. Give a database password you can remember and a project name. Maybe just call it Scrimba Customer Support AI Agent. Once you've created the project and you've created the organization, you're going to see an interface like this. And what you want to do is scroll all the way down to the bottom left, click on the gear icon so you can go to the settings. When you're in the settings, under project settings, move your mouse all the way down to API keys, click on API keys, and then you're going to see this interface with what's known as your public key, which is safe to use in your browser, and your service role key, which essentially allows you to bypass row level security and access any data in your database. For the sake of this course, we're just going to take both of them. So make sure to copy both the public key and the service role key. So you click reveal and also copy that as well. Once you have both of these values, you want to come back, click on the gear icon in the bottom right of your Scrim, and you're going to get the interface here. You've already saved your OpenAI API key. So save your public key as the value for superbase underscore URL, and then superbase underscore service underscore role underscore key, place the value of the service role key here. So at this point, you've set up superbase URL and the superbase service role key. Now let's jump into the actual code. So now at this point, you should have your OpenAI API key and your Superbase service role key. And so this will allow you to create the Superbase client so you can access the database. As you can see, we've stored some dummy text, and this text can be replaced with your own documents. But for the sake of demonstration, I'm just showing how we can take this, embed it, and then store it somewhere that we can retrieve later on. So different topics, Magna Carta, Apollo, the history of computing, and so on and so forth. Here we have the logic for inserting the information from this text into the vector store. And here we have the main function. Now, before we proceed, you need to go to created underscore tables.sql and copy this SQL command, which will help you to enable PG vector extension and also create a documents table. You will pass in the content, any metadata, and the embeddings associated with the content. Remember, the model we're using is 1536 dimensions. So that is what we are going to pass in here. So command copy, go back to your Superbase interface UI. Now, previously you were in the settings section. Click on this icon, and this will open the SQL editor. When the editor is open, it's going to have a button for you to create a new command essentially, and just paste what you just copied in here and then click run. So once you've run inside the Superbase editor, it's going to create a table and it's going to create this extension. And so you will be able to see a table like this. Now, you will initially have an empty table until we finish this exercise here, but you should see a documents table here. Once you've completed this task, before you run the command, I'll just walk through what's going on here. Essentially, your source documents are in this directory, so we're going to fetch it. We're using text embedding 3 small as the model. Your table name is documents as per what we stored here. Here is an option. It's just a toggle I created that allows you each time you run this script to delete all the contents of your database. It's just good for the sake of demonstration, because then each time we rerun this or you rerun this, you don't have to think about merging content from a previous run. If you turn this to false, then every new run will just add new content to the documents table without removing previous content. So all we're doing here is going into the path, fetching the text, and what we're going to do is embed the file content. So you remember in the previous lessons, we discussed using the embeddings function to create embeddings based on content. So now we're just simply repeating that exercise, except we just fetch the file content from the text file. We pass it here as input, and then we store, or we are creating objects that have content in the same object as the embeddings and metadata, which include the source file name. And so this is very useful because when you later on retrieve the relevant documents, you're not just retrieving the content, you're also retrieving associated metadata, which you can then use to basically see where the information came from. So once we're done creating the embeddings, all we're doing down here is using the Superbase client.from, basically just points to the table and then insert command. And we're just going to insert all the collected documents. And that's it essentially. So if you go to index and you've done everything as per your API keys, all you need to do is click run. We should, as you can see, as per the terminal, ingest with the source as text.txt, and you can see the embedding attached. We've uploaded one document to Supabase table documents. So then check your Supabase documents table, make sure this text is there. You should see a table that consists of this text as a content, metadata, which should be source text.txt, and then the embeddings. See you in the next lesson. All right, so based on the previous lessons, you should have already been able to create embeddings, understand what the role of the vector store is. And so we've taken the documents, and we will visit splitting shortly in another lesson. But essentially, we've taken the documents and we've embedded them and stored them in Supabase. So you should have already done that in the previous lesson, and the documents should be in your documents table in Supabase. Now, in this lesson, we're going to go over this step, retrieval. The user asks a question. We convert the user's question into embeddings. We go into the vector store. The vector store is going to perform its similarity calculations to see which embeddings in the vector store are most similar to user's query. We retrieve the relevant portions, and then we pass the prompt, the query the user provided, plus the context of the relevant docs in a final prompt that's sent to the model to generate an answer. So this is essentially what we're going to work on in this lesson. So jumping into the code, I will just walk through the changes we've made. We still have the documents folder. In config, we still have Supabase client and OpenAI. We've added a few things in the utils, which I'll come to shortly, but one of them is the prompt that's going to be sent to the model, which is going to pass in the user's question alongside the context. This context is what we are essentially trying to retrieve from the vector store based on the user's question. So essentially, just to take the magic, this is what we're going to send to the model to generate an answer. And so our job is to essentially solve for this equation because we already know what the query is and we already know what the rest of the prompt is. We just need to fetch the context. And so we have this new logic called retrieve similar docs that will essentially help us to retrieve the relevant documents from the vector store. But before we do that, please go to created_tables.sql. And now I have new logic. Now, in the previous lesson, you went to the Supabase editor to create the documents table. This time, just copy this whole thing, go back to the editor, and run it again. What is this doing? Essentially, this is a database function that is going to help us to find the relevant embeddings that are most similar to the user's query. So you have other variables here, which we'll be able to pass in. Later on, we'll be able to say, okay, how many results should we return? What is the threshold, right? So all embedding similarities are between 0 and 1, where 1 meaning that the two embeddings are very similar to each other, and 0 means that they're similar. So maybe you don't want to pass in too much polluted content into the model's context so you can adjust your match threshold. I've set 0.3 as default. And then here is just an optional filter that allows you to maybe filter based on metadata. And this is what you're going to get back from this match documents function. Cosine similarity essentially is the calculation I discussed that is performed to essentially see which embeddings are as close as possible to the user's query. Remember, the user's query is going to be converted to an embedding. We're going to the vector store to also see which embeddings are similar to the user's query. So essentially, this is a database function that once you've created it, we can then create this function here. So Supabase allows for the ability to make remote procedure calls to database functions. Remember, you created this match documents database function. So we can make a remote procedure call here, and then we can pass in the query embedding as we define here, the match count, match threshold, and filter. In this case, I'm only going to pass the query embedding and the match count. And to get the query embedding, it's just what we've covered previously. You're just creating an embedding based on the query passed in as a parameter in here. So the query comes in, we generate the embedding response, and then we pass in the embedding into the remote procedure call to trigger this database function that was created And we've got in the constants fixed variable just to fetch 5 similarity count. Now, we have also defined a new variable called the answer model. Why? Because in the previous lessons, all we were doing was just retrieving the relevant documents. We didn't do anything with them. This time, we're going to take an extra step. So if you come back here, if you just focus on retrieving the documents, which is calling the retrieve similar docs based on this question, which is covered in this document here, this text.txt. If I click run, what we're going to see in the terminal is we should see that we fetch the content. And this is what we expect. We expect an ID. We expect the content, which will be the entire document, because remember, we embedded the entire text. We did not split the text into chunks. So there's only one block of text, and then we've got the metadata. And this is the cosine similarity I discussed previously. As you can see, it's saying 50-50 in terms of how similar it is to the user's question. And that's because this text contains both the relevant information to answer the question, which is right here in 1843, but it also contains a bunch of other irrelevant information that has nothing to do with the question. So that's why the similarity score is relatively low. So now we've retrieved the docs. The next step is to essentially create the prompt. And as I discussed previously, we are going to take these relevant docs, access the content property. That's what this function is doing. So we get the full string, and then we pass in the context and the query to construct this final prompt that the model is going to use. Remember, every time you make changes, just Control S or Command S. Once we've created the prompt, we are now going to send the prompt to the model and then console.log the response from the model. So now we are going to press run just to generate the output. And so we're going to send the entire prompt to the model. Here we go. In 1843, Ada Lovelace published notes describing algorithms. She's often called the first computer programmer. So that is essentially coming from this block here. It's providing an answer based on what is stored in the text. And this is very different to just simply retrieving the relevant docs. You're now able to go into the vector store, retrieve relevant information, pass it as context in the final prompt, send the prompt to the model, and generate a final answer. So that is it in a nutshell. You can play around with this, and when you're ready, I'll see you in the next lesson where we're going to discuss how to split this into chunks so you can have more relevant chunks of text, embed those chunks, and retrieve the relevant chunks, as opposed to, in this case, we just retrieve one big block of text. But before we do that, let's have a challenge. So at this point, you should have embeddings of documents stored in your Superbase. And in this lesson, we'll be doing a short exercise where you're going to recreate building the retrieval mechanism we've discussed in previous lessons. You take a user's query, as we have here. You embed that query using OpenAI's embeddings function down here. Then you retrieve the relevant docs from Superbase, calling the RPC match underscore documents function, and then you return the relevant docs. When you have the relevant retrieved documents, we already automatically create them into a single string. You create the prompt using the getRagPrompt function from here, and then you pass in that prompt into OpenAI's model to generate a final response. And then you can see the relevant constants here, including the model, the similarity match count, and the embeddings model, all here ready to be used in the functions provided. So in the end, when you run this function, you should be able to see the final generated answer based on the user's question. Now, two things for housekeeping here. Number one, make sure when you're making changes, you press Command S if you are on Mac or Control S if you're on Windows to save your changes. And the second thing is make sure the question can be answered based on the context in the documents that you've stored in your Superbase. So, for example, if in Superbase you've stored content from the Great Fire of London from the previous text written lesson, then just keep this. If, however, you don't have that and you have something else, or from the prior lesson, just make sure you change the query so that you can fetch relevant documents in the vector store. Okay, with that being said, go ahead with the exercise and I will come back to provide a solution shortly. Good luck. Hopefully you didn't find that too challenging. Let us start down here by first of all getting the embeddings response. Remember, OpenAI provides an embeddings function, and all we're doing here is passing the embeddings model name, and we've got the input, which is the user's query. So done and dusted. We just need now to access the embeddings response. I believe that should be data 0 and embedding. So now we should have the embedding corresponding to user's query. Down here, you just want to get the documents and the match error from calling superbase.rpc. And remember, the database function is called match documents. And then we want to pass in the parameters. First of all, you are passing in the user's embedding, so the embedding of the query, and then the match count, how many relevant docs to return, is limited to 5, which was passed previously. Okay, so now we have embeddings, relevant docs, and now we want to return the relevant documents similar to the user's query. Now, further up here, we want to take the retrieve docs. This is the context. And now we want to pass in the query and the retrieve docs to construct the final prompt that will be used by the model. And then finally, construct the response. So the AI response is going to be taking OpenAI responses, create, and then we're going to pass in the model, answer model, which is GPT-4 in this case, and you can change that later on. The input is the prompt. Further down here, we're just going to console.log response.output underscore text, and that should be it in a nutshell. So AI response. And now let's click run and see what we generate in the terminal. Voila. The Great Fire of London destroyed some 13,200 homes. That's exactly what we expect based on the relevant documents. We can see that that information is contained here in this chunk. Okay, fantastic. Well, great job so far. You've covered going over embeddings, recap on using the vector, retrieval, splitting, using OpenAI. And now in the next lesson, we're going to move over into exploring Vercel AI SDK, a library that will help to greatly simplify and abstract key logic for building AI agentic apps. See you soon. Okay, so in the previous lesson, you have learned how to essentially construct a retrieval mechanism that will take a user's question, create some embeddings of the question, go into the vector store and compare the user's embeddings against what's in the vector store, retrieve relevant documents, create the prompt and context, and send to the model to generate an answer. Now, we want to explore briefly an intermediate step, as shown previously, of text splitting. And essentially, what is this? Now, imagine we have this long document. This is just a passage from historical information on the Great Fire of London in 1666. Now, if you simply pass everything into the vector store and embed all of this as one chunk, what's going to happen is when you ask a question, as we've seen in previous situations, the vector store is literally just going to return this entire document. And this can be problematic for various reasons. First of all, maybe the user's question is only could be answered by a particular chunk of paragraph. And so by giving the model the entire context of the entire passage, you're essentially increasing the odds that it misses out on crucial details that may be required to answer the question. It could be as simple as this sentence right here, but the model might get confused or conflate with all the other information around that text. The second challenge with simply just grabbing the entire block of text is that your model might not be able to handle the full context window. As we know, models are limited by context window of a number of tokens or characters they can pass in for any generation. Now, obviously, in this case, this is relatively smaller passage or chunk of text. But you could have, for example, a PDF of hundreds of pages, of hundreds of thousands of characters, and you will not be able to pass everything into the same context window. So in order to overcome this issue, we need to find a way to essentially split our document into various chunks, embed each chunk, and store each of them in separate rows in the table in Superbase. So the only adjustment, or the main adjustment I've made here, is to introduce this new function, which is a very, very basic, simple text splitter. It's going to take the text, some sort of chunk size you provide, how many characters to split the text into, and overlap, how many characters should overlap between each chunk. This is very, very basic and only for demonstration purposes. As a matter of fact, in this course, for the most part, we are not going to use text splitting, but it is important for you to understand how it works and why it's important. So once we've done the text splitting or create this utility function, the observed documents logic has been updated. So if you scroll further down, you'll see that instead of just simply fetching the entire text and embedding that, we first of all the document into chunks, and we have stored the chunk size 2000 characters in an overlap of 100, similarity of 5, and a threshold of 0.5. And so when we observe this document, we are essentially going to chunk. Then after we create the chunks, we are then going to embed each chunk. So the only difference between this example and the previous time was previously we just took the entire document and we embedded it. And this time we are taking each chunk and we're embedding each chunk, and we are adding a row for each chunk. So essentially, you will end up with a table with multiple rows, and each row is representing 200 characters of the block of text and the associated embeddings. So I'm going to run this function now. Go to your index.js, and you can see the question, how many houses were damaged? And it's a very specific question inside the corpus of text, which can only be found in one sentence. So we need precision. And so this is a good use case for splitting. So I'm going to click run in the top right. Let's see what we find. And you can see we've now embedded, we read 5,988 characters. We split into 4 chunks, and the different chunks were embedded into the vector store. Okay, so now you have 4 rows. You can verify in your end. Instead of that one row with one block of text, you should have different rows now with each chunk. So I'm going to comment this, and let's uncomment this whole block here. This is just a repeat of everything we learned in the retrieval lesson. We're going to go in the vector store, pass in the user's query, but you're going to notice something different this time. Actually, before I generate this, let me just demonstrate what I mean. So now we're going to run again, and notice that we have fetched more than one chunk of text, right? In the previous lessons, you saw how it was just one block, but now you can see it's an array of multiple objects, and each object represents a chunk of text that was embedded. And each chunk has a similarity score assigned to it, saying how relevant it is to the question. And you can see that based on the query provided, we said how many houses were damaged during the Great Fire of London. And so you can see that this chunk already has the answer to the question, because the answer to the question is 13,200 houses. And so this chunk has already succeeded in fetching the relevant portion. So imagine you had thousands and thousands and thousands and thousands of characters and words, and what the embeddings approach has done is allowed you to just quickly retrieve this small chunk so we can precisely provide this context to the model. You can see the similarity scores all above the match threshold that was set in the constants file. So you can see we have an array of different retrieved docs. Okay, now we want to just complete the remaining steps as we did before. So just uncomment this, and essentially we're creating the prompt with the chunks of text retrieved, which is all of these text combined together as the context string. We then essentially pass in this prompt to the model and generate a response. So let's click on run and see what happens. So now we're running, and waiting for the response. And according to the context provided, approximately 13,200 houses were destroyed. And that's exactly what we expected based on the information here in this sentence right here, or paragraph rather. So now you've seen how we've been able to basically take a relatively large corpus of text, split into chunks, embed those chunks, and now we're able to have more precise answers to the question. So I hope this gives a good overview on dealing with inserting data into your database as embeddings, retrieving them, and answering questions. In the next lesson, we're going to explore the Vercel AI SDK and discuss how this can streamline and make it much easier to build AI agentic apps. So, as discussed earlier in this course, we would later on interact with Vercel AI SDK. Now, what is Vercel AI SDK? It is essentially an open source library by the Vercel company, the same group and team behind Next.js, that essentially provides a unified interface to interact with LLM providers. You can plug and play different providers with the same interface. You can access very useful functions that are used for building AI apps and agents, for generating text, generating embeddings, generating structured output, generating different steps that an agent can take. And it just simplifies the entire process. So it's a very useful library for us to use, especially in this course. For example, you have a very simple generate text interface that you can import from the SDK. You provide your model and a prompt. That's it. If I want to swap OpenAI with Claude or any other model, it's very easy to do so, as opposed to going through each of their documentations and finding their own different styles of generating an AI response. The same thing for embeddings. You can simply import embed from Vercel AI SDK and use that unified interface. It doesn't matter what the model is, you can still get the same outcome. So now if we jump into the code, the config is still the same. Package.json, we've installed the AI SDK both here and here. And then finally, we have imported the OpenAI model that we're going to use as our AI model. So the key difference now between this and previous lessons is you are not using OpenAI's interface anymore. You're using the generic interfaces provided by the AI SDK. For example, here we want to generate text. We provided the OpenAI model, and the prompt is write a brief poem. So if I run this, we should see a brief poem that's been generated. The same applies to embedding. So let me comment this out and uncomment this. To generate an embedding, you import the embed function from AI. You call the OpenAI.text embedding model and you just pass in the embedding model. The value is just whatever you want to embed. So this text will be converted to embeddings. I'll click run again and we see the text has been converted to embeddings. You will see we have a full 1,536 items representing the embedding for the text. So all we've done essentially is taken the same concepts, but instead of hard coding it to OpenAI's way of doing it, we have these generic interfaces. And this is going to be very useful for us moving forward as we begin to build AI agents that may potentially want to use one or more models depending on the strengths and capabilities each of them have. So, that being said, we've covered the basics. I'll see you in the next lesson where we dive deeper into Vercel AI SDK. All right, in this lesson, we're just going to do a brief exercise to recap the basics of using Vercel AI SDK. So the challenge is you are going to essentially replicate the logic before, but we're going to have a twist. So the goal is to generate text and embeddings using Vercel AI SDK. You are going to implement the generate text interface in here, pass it into a prompt to the model to create a recipe for your favorite meal, and then you're going to return the generated text from the model. That is the recipe. Afterwards, you're going to have that value assigned to text to embed, and text to embed is going to be passed into the generate embeddings function, which is ready to take that text. Then we're going to embed that text using the embed interface. So that's the objective of this challenge. I'm going to give you a couple minutes to do this. Go ahead, and once you're done, I will provide a solution. All right. Hopefully didn't find that too challenging. So let's kick this off. So the first thing here, if you remember from the previous lesson, is we want to create an interface using the Vercel AI SDK generate text. So we're going to have the text extracted from the await generate text. And inside here, we are going to pass in the model, which is the AI model already up here. So GPT-4.0, and then the prompt. So create a recipe for making pizza. So whatever your favorite dish is, the idea here is to ensure that it's whatever your favorite, so say pepperoni pizza. Okay. So now we're going to send this off to the model. It's going to give us back the text, and I'm going to console.log and say generated text, which we'll pass in here. And then finally return the text. Okay, so that way you can uncomment this, and now text to embed should be the value of the text. So that's phase one. And then phase two is use the embed interface to generate embeddings. So we will already have the text to embed passed in as a parameter into this function. So all we have to do is extract the embedding from await embed, the model, which is OpenAI dot text embedding model. And then you're going to pass in the embedding model. So this is the embedding model name. Value is going to be the text to embed. So this is what you want to embed, which we passed in, which is the generated recipe of your favorite dish. And then here we're just going to console.log the embedding generated. Okay. So now we're going to run and see what happens. We can see generated text. Sure, here's a simple recipe for making delicious homemade pizza. Pizza dough, teaspoons, sugar, olive oil, salt, pizza toppings, and so on. And it's got instructions. We take all of this text and we generate the embeddings from the text. And that's it in a nutshell. So now you've got the basics of how to use Vercel AI SDK to generate text and generate embeddings. In the previous lesson, we discussed briefly the basics of Vercel AI SDK to generate text and generate embeddings. But one of the more useful use cases, especially in the cases of building agentic AI apps, is the ability to generate structured output. So giving the model instructions to give you back structured output, so then you can use that for something else, maybe pass into another function that will call an API, retrieve data, or pass into another chain of the model so it can do something else. Now, one of the useful interfaces that Vercel AI SDK provides to do this is the generate object interface. This is an interface that allows us to instruct the model to generate structured output in JSON format based on a predefined schema. When we mean schema, we just simply mean you're defining the data types, the properties you want, and the data types. Do you want a string, array, objects, and so on and so forth? And so, for example, down here, we have a function called basic structured output using this generate object interface to essentially instruct the model to provide a structured JSON output of a recipe for pizza with the schema of object that contains name, ingredients, and the steps for creating the recipe. And each property is defined by data type. So string, ingredients is an array of objects with the name and amount, and so on and so forth. And we're using this Z. Z is imported from a library called Zod. Zod is a popular library used to define schemas, used to define data structure interfaces. So we're just simply accessing and using Zod to help us to define the schema. So Z.object simply means object. You're creating a schema. You're basically saying, I want an object. Z.array means you want an array, and Z.array with Z.object inside means an array of objects with name and property as strings. So when we tell the model generate a pizza recipe, we expect back a structured JSON object that contains name, ingredients, and steps. So let's run this and see what happens. Okay, so we're now running this. We've sent the instruction to the model. Please generate pizza recipe and give us back to structured output. And here we go. The name, which is a string, which is what we expected. The ingredients, which is an array of objects with name and object as strings, exactly what we expected. And steps, which is an array of strings. And that's literally how you can instruct the model to give you back a JSON in a structured output. You can see how this can be very useful to then instruct or pass on to another step in your program to invoke something else and create a chain of prompts or a chain of actions that's more agentic by nature. Another use case for structured outputs is classification. Now, in this example, we gave a plain instruction and left the model to exercise some form of creativity. But classification is usually binary. So in this case, we want the model to classify the customer review using either positive or negative. So if you pay close attention, we're using a type enum. Enum is just a special data type that enables a variable to be predefined constants. So you can have more than one or two or even three or more enums. But in this case, we want the model to give us a schema, provide a JSON that contains the reason for why it's deciding it's positive and negative and whether the type is positive or negative. We also provide describe. Describe is just a useful property added to the Zod schema to just help the model, guide the model to know what you're looking for. So here, I'm just further emphasizing that this is the sentiment of the customer review. And so again, we use the generate object interface and provide the model, schema name, the description of your schema, the shape of your schema, what properties you expect back and the types of those properties, and finally the prompt. Let's run this and see what happens. Okay, so here we go. Reasoning. The statement indicates satisfaction as the app performed as anticipated and type positive. And so we were able to classify the text provided by giving the model instructions using the generate object interface to give us a structured output and providing the enums of what we expect. And so you can start to see how this can be very useful for classifying customer reviews, classifying customer requests, customer service. The structured outputs gives us the ability to provide more structure so that we can take and manipulate data types to do something down the line. So in the next lesson, we're going to go over a brief exercise so that you can put this into action and begin to put this in memory as well. So in the previous lesson, you learned how to create basic structured outputs using Vercel AI SDK. In this lesson, we're going to do a brief exercise just to get you used to how the interface of generate object works and how Zod works. So the first goal is to build a Zod schema. You're going to place a simple sandwich order. All the instructions are down here, including what each property should be and what the data type of each of them should be as well, and steps have been provided. Once you've completed that for this function, you want to uncomment here and run. After you've run, the next exercise is to build a Zod schema for classifying a short message. Again, all the instructions have been provided here. How to classify a short user's message based on what's being sent, what the message is. So this is the message that we are using, and you will complete this as well. So I'm going to give you a couple minutes to work on this. And once you're done, I will provide a solution. Good luck. So hopefully that wasn't too difficult, but we will go through everything slowly right now. So let's start off with the sandwich order. As you can see, per the instructions, you can see the different data types as expected for the required fields to fill into z.object, which you will then pass in as the sandwich schema. So let us begin. The first thing is the size. So we want size and we want an enum. Remember, an enum is a constrained data type. So we can just pass in small, medium, and large. And you can also provide a description just to help the model as well, which is overall size of the sandwich. The next is bread. So as we said up here, bread is a string, so that's pretty straightforward. z.string and describe this is the type of bread, example, wheat, white, etc. The next data type is toasted. That's a Boolean type. So toasted z.boolean describe, and this is whether the sandwich will be toasted. We have toppings, array of strings. So the data type has been provided to you here already. So you're just passing toppings, z.array, which is an array of strings, and then minimum one, at least one provided here. I think this is complaining because we didn't pass a comma there. And describe one or more toppings like tomato, lettuce, pickles. And finally, the notes. So it's just an optional string. So you're going to do z.string. Then you're going to pass an optional. So you're just letting it know it's optional, and optional free text notes like cut in half. And so the prompt is here as we have provided previously for you. We have the sandwich order, simple sandwich order, the schema has been provided, and the console.log. So we're going to scroll up here, uncomment this, and run and see what happens. Okay, so here's the structured output returned by the model. We can see the size is small, the bread is sourdough, as we have the different choices here. Okay, so small sourdough bread, toasted is a Boolean, says true, toppings, an array of strings, exactly what we wanted, and notes, which is cut in half. So that is the basic structured output. Moving on to the next exercise about classifying the short user message and to complete the message class schema that has been provided to you here. So let's start off with reasoning. So reasoning is a string, and let's say describe, and this is a brief explanation for why this label fits, or however you wanted to describe that. So classify user's message, we're providing a reasoning, and then we're going to provide the label. The label is also an enum. Let's put the comma here so it stops complaining. And this enum is going to take a complement, complaint, and is going to take a question as well. So we've got the reasoning, and then we've got the label, and let's also provide describe so that the model has a better description of what we want to achieve here. So high level category of the message. So this is the message schema. And then you got the message here. You could also have a group of messages. So you could have a loop for basically an array of messages, and then for each message you can loop over and generate the object for that particular message. So now we have the generate object. Now classify the user's message below. It's the prompt sent to the model. And now we uncomment classification structured output exercise, comment the basic structured output exercise, and now we're going to go up and run, and we should see the label is complaint. The reason is the message expresses dissatisfaction with the app due to technical issue. So there we go. So you've been able to implement two types of use cases for structured outputs. One where you're able to essentially provide a prompt to the model to construct a JSON of the data types you want for multiple properties and multiple data types. And the second type, which is more focused on constrained classification. So I hope this was useful. Keep practicing, and I'll see you in the next lesson. So in the previous lessons, we've covered the basics of Vercel AI SDK, generating text, generating embeddings. We covered structured outputs and how you can effectively provide an interface that allows us to instruct the model to provide a JSON in the structure that we want. But where is this all pointing to? Where does this all go to? Well, it goes to eventually building agents that are able to execute what's known as tool calls. Now, what's a tool and what's tool calling? If you've never used function calling before, essentially tools are just actions that a model can invoke. So we take an instruction, we give it to the model provides some sort of structured output, and then we take that structured output to invoke a function. We pass that in as a parameter of some sorts, and then we're able to invoke another function. And so the results of these actions can then be reported back to the model, and then the model can then generate a final response. So how does this work in a nutshell? Let's use this basic weather example to illustrate what's going on. Remember, we've already covered using the generate interface in the previous lesson for structured outputs. And so what we want to do now is use a generate text interface provided by Vercel AI SDK. And what this expects is model, tools, and a prompt. Now, we've already covered schemas and defining schemas, constructing schemas in the previous lesson. And so essentially, we provide the model, which is already defined here. Tools are the functions that you want to invoke based on the structured outputs the model generates. Remember, in the previous lesson, we learned how to provide a schema to the model and how that schema would be generated as JSON. Well, all of this logic is just encapsulating defining the schema in this tool. So this tool will contain description. You want to get the weather for a location, the schema that you want the model to enforce. So you want the model to enforce the location as a string in an object. And we have this execute function. This execute function is then called, passing in the location into the parameter to invoke this function. The results of this function will then be displayed. Okay, I'm going to run this because I know it might not be too clear right now, but hopefully this example will make it make sense. So remember, all a tool is a function or an action that the model can invoke. It is essentially a way of taking structured outputs generated by the model and then extracting that to then pass in as a parameter, as we've done here, so we can invoke a function. So we have the tool call here, and the tool call has an ID, and the tool name is weather. Okay, we are trying to get the weather of a location. The user's provided a prompt, what is the weather in New York? The model sees this prompt and creates a structured output with New York as location. Location is then passed in to the execute function, and this is returned. Location, temperature with a random number between 50 and another value. So we can see here, this is the tool call, which has the input as the location New York because we provided a schema as we learned in the previous lesson. And now we have the tool result. This is the result of calling this function. So all of this is happening under the hood. First, the model generates the schema, then it's passed in as a parameter, the function's invoked, and that's why we have the output as location and temperature is this random value. Okay, so that is the difference between a tool call, which is more just a structured input, and the tool result, which includes the result of invoking the function. So you can imagine that this could be an API call to your database or any other place. The key point here is the parameter used to invoke the function was a structured output generated by the model through the prompt that you provided. Okay, now, what if you want to provide multiple tools? Sometimes to get the results we want, it's not sufficient to just provide one tool. So let's say in this case, we want a situation where we have two tools. We want to first get the weather in a location and then get the tourist attractions in the location. Now, all of this should be familiar to you because the schema is defined in a way familiar from the structured outputs lesson. We want to tell the model that we want an object that contains city as a string. We also want to execute this function with the parameter passed in, the input schema passed in, the city extracted, and we want the city, and then we want to return these attractions. These are hard-coded values. And so if I go further up here, let's run. And when I ask the question, what is the weather in New York and what are the best attractions to visit? The model is going to see this. First of all, the first tool, which is the weather tool, is going to see the schema and extract New York as location, pass that in here and return this value. The second one, which is best attractions to visit, the model is going to see that and realize it needs to invoke the city attractions tool. Looking at the descriptions, it's going to extract New York as the city and it's going to return New York and the attractions. Let's see what happens. Okay, this time, instead of one tool call and one tool result, we see tool call 1, which has the location New York, and tool call 2, which has city New York. And we also see the tool results for both of them. First, we have the output location New York with temperature 43. And the second tool result is going to be the city attractions tool result, which is the New York and the values here. So you see how we've gone from generating structured outputs to now being able to take those generated structured outputs and be able to use them to invoke functions so we can get back data. Now, of course, all of this would not be complete without a way to generate a final response from the model. Remember, the whole point behind retrieval augmented generation is the ability to fetch context outside of the model's training data so we can pass it back to the model in the prompt and generate a more context relevant answer to the user's query. So the whole point behind this is not just to be left alone with this tool calls and these tool results. Perhaps, like I said, you've executed called an API, you've retrieved the relevant information, but now we need to pass that relevant information to the model so we can generate a final answer. And so this is where this last step comes in. And Vercel AI SDK provides these useful interfaces, as we've seen previously, the generate text, the tool interface, and so on. And now we are able to use what's called the stop when. So as it says here, by default, our tool calls will just return the results of executing the function, which is nice. But we need to take that to the model to summarize the tool results. What the stop when property does is it basically tells the model to loop over itself again and take X number of steps beyond just generating the tool results. So after the tool results are returned, we can then tell the stop when to basically take another step to provide the tool results to the model, and that would tell it to generate the results. So the way to think about stop when is just how many times to invoke the model in the process that we're currently running. So here we have 3 steps. So step 1, it will invoke the tool results here, create the structured outputs here, and then the execute will be called, which we've seen. This is the second step. And then the third step that we want is for the model to summarize the results from the data that's been returned from invoking these 2 tools. So that's why the number 3 has been passed here. And then we have other logic to extract that. So let me run this. And you can see we've essentially extracted the tool results, and then the final result generated by the model is what we can see here. So let's scroll back. We can see we've logged the tool calls, and as we expected, locations New York, cities New York. The model has basically seen the results of the tool results and aggregated, summarized what it's seen in a more human way. Current temperature is 72 degrees, and it provides the tourist attraction. So this is not too different from what we've learned with embeddings, storing embeddings, retrieving relevant documents, passing as context, the model generates an answer. The difference this time is that by using tools, we can provide custom functions. These functions can also call the vector store to retrieve embeddings of relevant documents, or it can call an API, it can call your database. It just gives a lot more flexibility for where you're retrieving context to pass into the model. And you can see how this allows you to build more powerful, complex, and multi-steps agentic applications. So in the next lesson, we're going to go over some exercises to help you have a better understanding of how tool calling works. In the previous lesson, you learned basics of using the Vercel AI for tool calling. As I mentioned before, tool calling is essentially taking structured output from the model and invoking a function that you define based on the inputs constructed by the structured outputs. Now, in this exercise, you are going to practice this. We have the goal here to implement a single tool, which is essentially fetching a grocery item from this in-memory data. We're trying to mimic what would happen, say, if you had fetched data from the database to get the price, and also implementing a situation where you have more than one tool, so delivery ETA as well, and using the stop when in the third case. So for each of these, you have all the comments. So you would start with number 1, on comment, run it. Number 2, read the instructions follow the to-dos, and number 3 as well. So you should be able to go through all 3 of them. It should take you a couple of minutes to get through them. Make sure to Command S or Control S to save your changes, and then click run to run and see what happens. So best of luck. Take a couple of minutes to do this, and I'll be back with the solution shortly. Now let's begin with the first one. The first exercise here, the first challenge, is create a price lookup table that will take item string and return item price using the price table. So the first step is to define the tool with the Zod schema. And so we already have the tool here. Now to define the schema in here. So what we have to do is that the object is already open. So you're just going to pass in the string type into this input schema. Remember, we want the model to return an object of item, and the item being whatever it is we want to search. In this case, milk. So we want milk to be passed in here. The next thing that we want to do is to go ahead and implement remaining portion here. So this is the execute function. So all you have to do is uncomment this section here. We're passing in the item in, and then we are going to return this function here. So we should get the item and then price, which is then going to be from the price table. We're going to pass in the item passed in to lowercase just to make sure, and then fall back to null if we were not able to find it in there. So now we've got this price lookup here with the tool, execute, and then we pass in the item as a parameter, and then we return this item and the price from the item. And so now we can pass in price lookup into tools. So we just need to uncomment this, and price lookup is being passed in as a tool. And so when how much does milk cost is going to extract milk as the item, invoke the function, return the tool result, which will be what is returned by this function. With that being said, let us uncomment the first one, save and run. Okay, so as expected, we've got the tool call, which has the item as milk, is the input into the subsequent function as we discussed. The model was able to extract the item as milk as per the schema defined. And the tool result, which is now the price lookup, is going to have the output, which now includes the milk item and the price for milk, which is 1.59. And that corresponds to what we have here. Okay, so that's the case where we have one tool call. Let's move over to the case where we have two tool calls, and we want to introduce a delivery ETA that takes address string and returns a pretend estimated time of arrival. So here are all the instructions again, and we're just going to follow the sequence. So we have the tool interface, description. We want an item in string as we have, and here's the solution. Hopefully you didn't see this before the previous one. But now we've got this delivery ETA, which is the estimated delivery time. So we need to pass in the address .z string. That's the address is going to be a string. This is what we want the model to enforce. This is the JSON we want back. Inside here, we're just going to pass in the address. And then ETA is going to be a random number as assigned by this value. And then here, just remove this and pass in the address. So we should get back from this function an address and estimated ETA minutes, which is the random number generated here. And then based on the question, we should see extraction of milk, and we should also see an address extraction as well, which should be returned back in this delivery ETA function. So if we run this, make sure we first uncomment, we should see the tool calls and tool results. So let's see what the model is called. The first item extracted was milk. Okay, we expect milk to be extracted because we defined item. And so it's seen the milk and it's fetched tool call for the milk. It also made a tool call for bread because we also put bread inside the prompt. And finally, a tool call for the address, which was extracted from the prompt. Now we have the tool results, milk and the price 1.59. We also expect to see bread and the price, which is 2.49. And finally, the address and estimated minutes, which was calculated by the tool function further down. So I hope you're getting the hang of this. Essentially, all we're doing is using prompt, send into the model, give the model a schema so it can construct a structured output, take the inputs of the structured output, pass that in as a parameter into another function, invoke the function with those parameters, and then return the results back to the model to generate a final answer, which is the third and final exercise we're going to do right now. Because as I said before, having the tool results is extremely useful, but if you want to complete the process, we want the model to essentially summarize the results like we would do with RAG. You might not just want to retrieve the relevant documents from the vector store, you also want to synthesize that with the prompt so you generate a final answer. And so now we move over to the last challenge. We want the model to call the tools, receive the results, and then summarize them in the second turn using the stop when function. So we've got the price lookup tool, the delivery ETA tool, which is the, as we covered, passing the address, we're passing the item. And now we want to enable step count to count number of steps. Remember, the model is used to generate the tool calls once, twice, and now we want a third step where the model generates a final result using what the tool results have been. So models invoked once, step one, models invoked twice, step two, and model is going to be invoked the third time. That is why we are defining here as stop when the step count is 3. The prompt is I want to buy eggs and banana. Use tools to check prices and tell me total cost and estimate delivery time to 221 E Baker Street. So we have the tools being defined, the delivery ETA, and the results also being provided as well. So we are going to call this and see what the results are. And there we go. Final summary. The total cost for eggs is $3.29, as we can see in the dummy database. Banana is 0.59, so the total cost is 3.88. The estimated delivery time to the address is 26 minutes. And this was exactly what the user had asked for based on the prompt. I hope you found this useful. You can see how we've gone from a basic prompt to generating embeddings to the retrieval from the vector store to then exploring the ability to utilize tools to essentially extract information from invoking functions. And you can see how this is leading to multi-steps where a model can be involved in multiple steps to get to a final outcome, sometimes involving one or more functions based on inputs provided by the model, and then the model at the end helping to summarize the information. So I'd recommend you just keep practicing so you get a good feel for this. And once you're more comfortable, you can go to the next lesson where we're going to start piecing this together in building the final customer support AI agent. So in previous lessons, you've learned about how to use Vercel AI SDK to create structured outputs, generate embeddings, generate text, and also introduce tool calling. Now we're going to move closer towards the final project of building a customer AI agent. The first thing we're going to try to do is create this basic agent routing architecture, as you can see on the screen. Unlike the usual route retrieval, which we covered earlier in this course, where you embed the documents and then the user asks a question or retrieve the relevant docs and answer the question, which would be this typical path going this way, we are now going to introduce two branches. So it's no longer one direction. We're going to have binary. We are now going to give the model the opportunity to classify if the user's question requires a retrieval. So if it does require retrieval, we will continue to do what you've learned so far in the early parts of the course with retrieval. And if it doesn't require retrieval, we'll just answer the question directly using the model's trained data, whatever the model's been trained on. So let's go into the code. Now, what I've done here is introduce a couple of things. The first thing I've introduced is replacing all the primitive OpenAI library functions with Vercel AI SDK. So when we ingest or observe the documents, we are using the embed and the structure Vercel AI SDK expects. The same thing with retrieval as well. Again, we embed using embed from Vercel AI SDK instead of using the OpenAI primitive, because when we export from config, we are using the create OpenAI client from the SDK, not from the OpenAI library. So these are the key changes, which of course lead us to using generate text, which is the interface by Vercel AI SDK. We've also introduced some new variables in the constants file. For example, the classification model is what model we're going to use for classification to decide whether to perform retrieval or not to perform retrieval. So in this case, I'm using the same model for both, but you're going to find a lot of use cases where you might want to use different models for each of them, depending on the strength of the model. And here we've got knowledge-based description, which I'll come to in a second once I finish the quick tour. We've got all the different functions I'm going to showcase here, which I'm going to uncomment one by one. And then we've got a prompts file. Now, this prompts file contains all the prompts used in this example, from the prompt used to retrieve to the prompt used to classify, and so on and so forth. I'll come back to this in a second. The other introduction here is the docs. Now, in the docs folder, I have extracted the markdown various pages that Scrimba has in its help desk. So it has multiple web pages for providing FAQ and answers to usual support questions. So what I've done is I've scraped all those web pages, converted them into Markdown, which is friendly for models and embeddings. And so when we run this ingest documents function, we're really just looping through each of these, extracting the text and embedding each of them. And then for each of the embeddings and the text, they will get inserted into the database. So I'm going to embed and insert into my database snippets of some of Scrimba's help documents. And once I've done that, we are then going to perform a basic retrieval and then a classify and retrieve. This is kind of more agentic as per the diagram I showed you earlier. Okay, so let's start with ingest documents. In the previous retrieval lesson, you learned how to do this without Vercel AI SDK. As I said, the only difference is I've replaced with the embed interface, and there is no splitting and chunking here because we're just looping through each file. There's no need because each of them do not contain anything substantial per se. So we're going to clear all the contents of your database. And then for each file here, we're going to loop over them, embed, and then insert, and then have a metadata property, which is going to have the source as the file name. So this is going to be very useful down the line when you want to inspect the source of where the chunk is coming from, or you want to display it in a UI. And then we're going to insert all of them. So we're going to run this. Let's go back to index.js. So here we go, ingesting documents from the directory. We loop over each of them, read in the characters of each of them, and we've successfully uploaded 9 documents to Superbase table documents. Okay, as per what we did in the retrieval lesson, and this is what one of the objects looks like. You can see the metadata points to the actual document. Then, of course, we have an embeddings property, the text, and the metadata for each of these files. And that's all being put into the database. So we're familiar with this. Comment this out. Let's jump over to basic retrieval. Now I've got a question here. How do I access Scrimba Discord? Now, what we expect to happen is for this function to kick off. First of all, retrieve similar docs is going to take the query, embed the query, and then send the query to Superbase remote procedure call through the match documents database function, which we created earlier on in this course to retrieve the relevant docs based on the query. So that's what we expect to come back. So when we get this back, we're going to have these documents, the relevant documents. We're going to pass it to this combine documents function, which is essentially just going to extract the text and combine all the text together. We create the RAG prompt, which you saw in the previous retrieval lesson, essentially saying below is the context, answer the question based on the context provided. And then we're going to generate the text, again, using the Vercel AI SDK interface and console.log the generated text. Now, If I go here, we've got one support document about linking your Scrimba account to Discord and another one on how to join Discord. So the expected behavior is that we are able to retrieve the relevant docs from the vector store to answer the question, and then the model is able to provide a relevant answer to the user. So let's run again. There you go. So to access Discord, use this link. And that was in alignment with what we saw here as well. So it was able, as you can see, look at the relevant docs. So we've got similarity score 0.48 for this chunk, which is the can I download the code in a Scrim file. So it was able to pick up on that. It also picked up on this chunk here, linking your Scrimba account to Discord, which I showed you as well. And all this content was passed as context. And finally, how do I join Scrimba Discord, which had the highest similarity score. So if you remember in the first retrieval lesson where we covered match thresholds, you can actually set a threshold at the point of retrieval as another property here that will allow you to set a minimum threshold. So you could say only retrieve documents that have a similarity score greater than or equal to a certain number. That way, maybe we would cut off this one and only focus on the top two. But I left everything here for you to see that what we expect to happen is exactly what's happening. So if we go back, now we want to go to the last section. This is the classify and retrieve function. So what's going on here? This is a bit more involved than what you saw previously. So I'm going to take this slowly. So essentially, the main step is that rather than just send the query directly to do the embeddings in the retrieval, we want the model to exercise some form of agency. We want to classify the prompt first. So we want to give the model the prompt and then let it classify whether or not it's a general question. If it's a general question, we let the model just answer the question directly using its own training. Else, if it's a retrieval, then let it continue with the process. Embed the query and call the remote procedure call to get the relevant docs and so on and so forth. I've also introduced what's here as a fallback. This is a situation where, for example, we don't actually retrieve any relevant documents. So we will just send the text to the model to just generate an answer directly. So provided that we do get relevant documents back, we will continue to go through the process, combine the documents, get the RAG prompt, and so on and so forth. Something else that's pretty interesting here that I've introduced is we will also map over the retrieve sources and then give them a type as well as where the source is coming from. So this would put more structure into the retrieve doc. So you're going to get the answer and the sources from where the answer was generated from. If we essentially are running into some sort of error again, we will just default to generating a general answer. Okay, so that is the classification in a nutshell. Let's go a bit deeper into looking at the prompts that's kind of driving this behavior. First of all, the classification prompt. This generates the prompt for classifying the retrieval or general. We pass in the question and knowledge-based description, which is in the constants here. Scrimba, an online platform for learning to code. We are going to pass that in here. And this is the prompt, classify the user's question. The goal is to use a customer support knowledgeable base about Scrimba. If the question is about Scrimba itself or it's coding technical and so on. If the question is clearly off topic, respond general. Otherwise, respond retrieval. And now we send that question here. Classification is an open colon, and we send that off to the model. So this is the prompt to classify. As I was saying previously, you could actually put this in the context of a structured output instruction to the model. So it's an enum, it returns either general or retrieval, but I'm keeping it simple here for the sake of your understanding. Then we've got get general prompt. So it's just a direct prompt, answer the following question concisely, and the question is passed in. And we've got fallback and we've got the RAG prompt, which you're familiar with, your helpful assistant, answer the user's question based on provided context, and so on and so forth. So pretty straightforward. All we're doing is classifying the prompt, generating a retrieval prompt or a general prompt and sending that to the model to provide a final answer. A few other things to note here is the use of max output tokens and temperature. Here, we're just limiting the amount of text returned. We really want to force the model to essentially say response or general. And so 20 tokens is enough to do that. Temperature controls the randomness of the output, how much creativity you want the model to have. In this case, I want 0 because I just want retrieval or just give me general. I don't want the model to express any creativity whatsoever. So that is the reason for the introduction of these two properties and their values. And with that being said, let's jump back to the main section. And I'm asking the same question as well. And the behavior I expect to see is a log for retrieval. And so that's exactly what happened. How do I access Scrimba Discord? We classify the question, and the question is being classified as retrieval. We perform retrieval, we generate the embeddings, we retrieve the chunks, and we generate the RAG answer. And that's the answer that we get. Now you can see the retrieved docs here. These are the source documents, and you can see ID, content, metadata, similarity score, and type, which was all defined in the agentic retrieval file. Now, let's say I completely change topic. What is the capital of France? Okay, now what we expect is different behavior where the classification should be general. So let's run this. And now we're answering a general question, and the generated answer is Paris. The retrieved docs is null because we never went to the vector store. So you can see how we've gone from asking a query, we perform retrieval, and it was this kind of one-dimensional approach, to now we've introduced more agency. We're giving the model the opportunity to classify queries, and now it can route in different directions based on what the query is. So in the next lesson, we're going to go deeper into this so you can see how this routing can build up to the final customer support AI agent. The previous lesson, you learned how to route the agent's outcomes in different directions, either towards retrieval or to answer the question generally. In this lesson, we're going to do a brief challenge where you are going to refactor the logic for the agentic retrieval to introduce structured outputs, which you learned a couple of lessons ago using Vercel AI SDK. So we're going to go to that file where the agentic retrieval logic is and follow the instructions to use the generate object interface to create structured outputs so that we can classify whether the question or the query, as you can see here, is retrieval or general. So what you're going to do is hop over to agentic retrieval, and we have the classification prompt here already done, decision already assigned to classification, which is extracted from the object here. And all you have to do is fill in the gaps here, construct the schema property, utilize Zod and everything you've learned, including the enum types from the structured outputs lesson, and then also add a property for the prompt sent to the model. Once you've done that, make sure to Control S, Command S, save your changes, and then run. So I'll give you a couple of minutes to do that, and then I'll come back with the solution. Good luck. So let's work through this slowly. We know we've got the model already, schema name, schema description. So the next natural thing that we need to cover here is just the schema. And so remember, we're using Zod, so we need to construct the object that we expect to get back. The first thing I usually recommend is you passing the reasoning so you can see what reasoning the model wants to give. And let's describe and say we want a brief reasoning for the classification choice. Why is it going to choose retrieval or general? The next thing we want to do is define the type and z.enum. And now we're going to pass in retrieval, and we are also going to pass in general. So let's go here. Let's pass in general. So we've got retrieval and general as the enum types. And then we can also add a describe again to help the model, where we are going to say, is the question general or does it require knowledge based retrieval? And finally, number 2, add a property for the prompt sent to the model. we will just go down here, and we already have the classification prompt here, which we already constructed, and put a comma here, and voila. So I think that should be that. So we've already constructed all of this here. If we go back to index, that's been imported, ready to go. Click run, and we should classify the question as retrieval. As you can see, the reason here is the question is about Scrimba's Discord, which directly relates to Scrimba's platform and user support. We've got the type retrieval classified, and we generate the answer as expected. So practice this a couple of times and you're ready. I'll see you in the next lesson. In previous lessons, you learned how to use the OpenAI SDK to generate responses based on a prompt provided. This was using the inbuilt OpenAI Responses API, and Vercel AI SDK was able to wrap around that and provide a simple abstraction over that functionality. But aside from just generating text, the Responses API also allows you to file search or web search or computer use, interact with different web pages. You would essentially be able to invoke that tool directly using OpenAI's inbuilt functionality and get the latest results from a web search. And then you can pass the results on to the model. So you can see an example of return data from the web search tool. Let's dive into the code. As you can see, we've imported OpenAI from Vercel AI SDK. We have the generate text interface for generating text, as we have covered previously. And then we've got the model and the question. What is the latest OpenAI large language model? And as of today, it is GPT-5. GPT-5 is the latest large language model by OpenAI. First of all, we're using OpenAI responses, and then we're passing in the model. And secondly, and most importantly, we are passing in tools with web search preview and openai.tools.websearch preview with this brackets in here so that there's nothing passed inside. So this is just the syntax. And what happens under the hood is Vercel AI SDK will then interact directly with the OpenAI APIs in order to invoke the tools, and then the model's going to generate an answer based on the tool results. So essentially, this is an abstraction over a lot of the functionality we've discussed previously with tool calling and returning the tool results and having the model generate the answer. It's just being abstracted and simplified. So if we click run, all right, so we can see the text as of September 2025, OpenAI's latest large language model is GPT-5, and on and on and on. So this is the text generated as a result of context from the web search passed onto the model. If we scroll further down and look at sources, you'll see what was fetched from the web. So you can see the sources, type, URL, ID, title. And so the contents of these different URL was scraped, passed as context, and the model saw the scraped contents of these web pages and also saw what the question was, and based on the question, generated the final answer. So this is essentially the same mechanism as we saw in retrieval. We're still performing a similar behavior. We're going somewhere, we're retrieving context, we're passing that context back to the final prompt that's sent to the model. And so this is essentially how we can incorporate a tool for web search, and you can see how we can build on this and augment pre-existing agents with multiple tools and add one of those tools as web search. And so we're going to see how this works in the next lesson. So in the previous lesson, you learned about using the web search tool provided by Vercel AI SDK and OpenAI under the hood. It's the OpenAI Responses API being used as a tool to retrieve information from the web in real time. Now, in this lesson, we're going to look at how to combine the entire mechanism about retrieval, which you learned, going to the vector store, retrieving relevant information to answer the question, as well as the web search tool. So the agent is able to decide which one to use based on the question. Now, what is new? First of all, we have taken the entire logic for retrieving, and instead of having a standalone file where we run the retrieval, we've converted it into a tool. Remember, a tool is essentially an interface provided by Vercel AI SDK that allows us to define what exactly we want to invoke based on structured output returned by the model. Here, we will provide a tool that is going to retrieve relevant information about Scrimba based on the user's query. And so that query is then going to be passed in to do everything else you've learned in this course. We embed the query, then we query the Superbase database, and then we return the retrieved docs. So essentially, everything you learned about retrieval is now wrapped inside this async function and execute in this tool interface. Now, if we go to Web Search Retrieval Agent, we have two tools. The first tool is the knowledge base tool. So we've converted the entire vector retrieval mechanism into a tool. We also have the web search tool, which we covered in the previous lesson. And then we pass in the tools. And then we've got stop when, which was also covered in previous lessons with the max stop steps of 3. So the model is going to iterate 3 times to generate the tool results and finally pass in the tool results into context and then generate a final response. We've also introduced this new prompt function, get retrieval web search prompt. Here we pass in the knowledge base, which is Scrimba, an online platform for learning to code. And if you look at the prompt here, essentially just saying you're a helpful assistant and your primary goal is to answer the user's question accurately. And we just provide conditions. Use knowledge base search if this. Use web search if you need real-time information, and then answer directly if you already know the answer. And so this is just a prompt to encourage the model to return the appropriate tool based on what is required. All right, further down, we just have different logic to extract the sources. If it's a web search based tool call, extract the web title URL. But if it's knowledge base, if we went to retrieval step, then we're going to access the steps property inside results, which is the steps that were taken by the model invoking each tool results. And then we're going to check if it's knowledge based search. If it is, then we're going to do some extra extraction. And eventually we're going to get the retrieved documents, which was passed in through the knowledge base tool. This is what was returned here. And so once we get the retrieved documents, we're just going to extract all the stuff that we had embedded and inserted into the database. So the content, the metadata, and similarity score, which can then be used later on for filtering or removing retrieved docs that are below a certain threshold. Once we're done, we're just going to return the answer, the sources, and the tool used. So with that being said, let us run this. Here are the response to sources. So we can see the similarity score and the documents retrieved from the vector store. And then you can see the generated answer here. And this is all based on context. But most importantly, look at this. It was able to identify that this was a question that required retrieval, calling the knowledge base tool. And that was how it was able to get the relevant context and then answer the question. Now, if I switch this up, instead of the retrieval based query, we then ask the web search query, what is the latest OpenAI large language model, passed to the web search retrieval agent. Let's see what happens. So I'm going to click run again. Okay, so here we go. So we receive the question, we generate the text, and then we see web search sources were found. And we've got the full generated answer by the model. And then if we go further down, we can see the retrieved docs, which is the different URLs that were scraped to get content that was then passed as context to the model. So you could see how we've gone from learning about vector store retrievals as a standalone action. Then we went further on to learn about structured outputs, the Vercel AI SDK, talked about web search retrieval using the responses API. And so with that being said, in the next lesson, we are just going to do a brief overview and exercise so that you can put this into action. So in the previous lesson, you learned about using tools for web search and retrieval together. So the model is able to decide based on the nature of the user's query, whether to use web search or retrieval to answer the question. So now I want you to take this challenge. In the web search retrieval agent file, You're going to implement the missing tools logic to add the tools and then complete the empty generate text function. So if I go in using memory, try to add the two tools, so one for knowledge base and web search preview. And then here you want to fill in the generate text properties. So all the properties involved, including the model, the prompt, and so on. I'm not going to say all of them, but just try your best for memory, and I'll be back in a couple of minutes to provide the full solution. Good luck. All right, I'm back. So let us work through this. The first thing is we need the knowledge base search. This was the name that we provided in the previous lesson, and we're going to pass in the knowledge base tool, which is imported from here. As far as the web search, we want to make sure we use this exact syntax, web underscore search underscore preview. And then you're going to pass in the tools, web search preview. And remember, you open and you leave it this way. This is the exact syntax that's expected from the Vercel AI SDK. So now we've completed the tools, but we now need to fill in the generate text property so we can include the tools. So the first thing is we need to pass in the model, OpenAI responses, and then you want to pass in the tool calling model. You've already defined this up here. The next thing we want to do is pass in the tools, so the model has access to the tools, and then stop when. Remember, you want to step count the number of steps for the model to iterate over and generate results and tool results, as well as the final response. We also pass in a system prompt. This is just kind of to give the model general instructions to follow. You can either pass it as part of a string in the prompt, but we just separated it for good abstraction. And we pass in the knowledge base description. And finally, we pass the prompt. This is the question that's passed in as a parameter in here. So we save all of that back to index.js, run the function, and voila, we get the sources, URL, and the full text as well. So that's it for this exercise. Keep practicing, and I'll see you in the next lesson. We have now come to the final lesson, an overview of the Keystone project, which is the customer support AI agent. As discussed, this is trained on Scrimba's Help Center articles, which have been embedded and stored in the vector store, as we've covered in previous lessons. And so, for example, if I ask a question, how do I access Scrimba Discord? We should see able to access the knowledge base tool as we covered in the previous lessons, retrieve the relevant documents, and display to the user. And of course, we can click on view sources and see the different chunks or the different documents that were retrieved, the similarity score, and so on and so forth. So this is a UI display of a lot of the concepts that we've discussed previously. If I ask a question which requires real-time information from the web, because the support documents do not contain them, I can do the same thing. So how do I resolve the error node module not found? And again, similar concept, but this time it's going to go, and rather than retrieving or using the knowledge base tool, it is now this time going to go ahead and perform the web search. So you can see it's able to retrieve the answer to the question based on web search information. And so you see this dual choice between the model, between deciding, should I answer this question using my retrieval tool, go to the vector store, or web search? Now, before we walk through the actual code, let's look at the architecture. So essentially, all this going on here at a very, very high level is the user asks a question. Then we have some way to tell the model, hey, check if this requires retrieval. If it doesn't require retrieval of any form, whether it's real time or vector store retrieval, just answer the question directly. If the question requires retrieval, then we want to know if it's real-time information required. Because if it's not real-time information, then we can go check the vector store to see if there's sufficient context to answer the question. If, however, it requires real-time information, like the question I asked, or if I ask something to do with a latest package or library that I wanted to use in this context, then it will go to the web to get the latest documentation for their particular package. And so this is the architecture we have in place. So if we go back, essentially, just to walk through the key changes or new things that have been introduced that you're not familiar with previously. The first thing, as you can see on the screen, is we have an Express server, and this has been installed here. And this Express server essentially is going to serve as the API route from which the UI, when it's clicked, then JavaScript is going to send the text to this API route as the question. And then we're going to use the web search retrieval agent, which I'll show you in a second. And so it's listening on port 3000. So that's what the server.js file is doing. The config is pretty much as you've seen previously. And then we have constants also having the constants that you saw in previous lessons, including similarity match count, which is number of retrieved documents from the vector store to return back, and the models to answer, classify, and so on. We also have index.html. This is the HTML of what you can see here. And then we have the style.css, which is design, and the client.js, which is the JavaScript that is listening for clicks to ask. And when it gets the click, it will assist in showing the sources and sending a post request of the question to server.js. And then server.js returns back the answer. And then we have a bunch of processing going on here as well. The key new introduction to walk through is the web search retrieval agent. So what's going on here? As we covered in previous lessons, we have two tools, the knowledge base, the web search preview. And as you can see, we essentially pass in those tools to the generate text interface by Vercel AI SDK, alongside the number of steps you want to take, the prompt, which is coming from here. So you can see we've got instructing when to use the knowledge base tool, the web search tool, and when to answer directly. Parsing of the different sources based on the tool called, and then we return the answer, the sources, and the tool used. And this is the knowledge base tool, which we covered in previous lessons, in its separate file for handling the embedding of the question and then fetching from Supabase the similar documents. And so that's it in a nutshell. This is the complete workings of a customer support AI agent that is able to apply some level of intelligence based on tools provided and based on the prompt decide what tool to execute or not to execute a tool at all and just answer the question directly. So you can see how you can expand on this. You can add more tools for different things. Maybe another tool for a particular API that can retrieve information. Maybe another tool that performs calculations. Maybe more niche tools that are specific to different capabilities. You can expand on this. So don't stop here. There's so much more you can do to build on what you've learned in this course so far. Use your own support documents or even another completely different use case, but using the similar concepts you've learned throughout the course. So I hope you've enjoyed this course so far. Keep practicing and good luck. Right, congratulations on finishing this course. Let's recap what we've learned so far. You've learned how to create and store document embeddings of support documents into Supabase as a vector store. Then you learn how to build a retrieval mechanism to question answer these documents, retrieving the relevant documents to answer the question from Supabase where they were embedded. Then you explore the basics about Vercel AI SDKs, APIs to generate embeddings, generate text, construct structured outputs, and then execute tool calls based on whatever actions you wanted the agent to take. You also learned how to utilize OpenAI's web search tool and the function calling and to integrate that as a tool for the agent to implement when it wants to get real time information. Finally, you learn how to build a customer support AI agent that can intelligently classify a user's query and determine whether to answer the question generally, perform retrieval, or web search. Now, with that being said, my suggestion for a stretch goal is to refactor the final project for your use case. Now, perhaps you don't want to do customer support use case. So take the concepts of tool calling using the Vercel AI SDK and apply it to something else. Maybe you want to build your own travel agent. Maybe you want to build your own coding agent or an agent that will do something else that's very useful. You can apply a lot of the principles you've learned in this course to do that as well. So, with that being said, I wish you the best of luck and thank you for taking this course. Cheers.